Look up on a clear night, and the stars offer a scattered backdrop of distant suns. But the moon sits intimately close, a quiet companion casting shadows across our history. Yet, for all its proximity, we remain uniquely isolated from it. For the vast majority of human existence, that glowing sphere was unreachable, a smooth silver light tracking the passage of months and tides, locked away across nearly 250,000 miles of vacuum. That boundary broke in 1959. The Soviet Luna 3 probe swung behind the moon and captured this image, revealing a hidden hemisphere bombarded by deep impact craters and entirely stripped of the smooth plains that face Earth. Those first frames anchored the moon in the physical world, turning a mythological light into reachable terrain. Less than a decade after those robotic eyes mapped the far side, human beings were walking across the lunar dust. Escaping the pull of Earth required staggering mechanical force. Engineers built vehicles standing 363 feet tall, burning liquid hydrogen and kerosene to generate 7.5 million pounds of thrust just to push a tiny capsule outward. But the Apollo landings were brief. Astronauts lived out of thin-walled modules for a few days at most. They were scouts, plunging into an isolated and lethal environment, gathering rocks and taking measurements before racing their limited oxygen clocks back home. Today, the focus has shifted. The engineering architecture currently in development is designed to stay. The scouting phase has concluded, making way for the era of permanent cosmic habitation. Surviving here requires constant defense. The lunar surface is bombarded by solar radiation and micrometeorites, swinging between boiling heat and freezing cold, devoid of air. To overcome these conditions, missions like India's Chandrayaan-3 have targeted the most extreme zones, the permanently shadowed craters of the lunar South Pole. This graphic outlines the complex orbital mechanics that guided the mission. It maps the series of elliptical maneuvers that gradually raised the spacecraft's orbit before injecting it onto a transfer trajectory toward the moon. This diagram shows the Vikram lander, mapping out the precise sensor suite, including laser altimeters and velocimeters, that worked with throttleable liquid engines to execute a fully autonomous touchdown in that harsh terrain. The objective of exploring this frigid region was validated by the confirmed discovery of vast deposits of water ice trapped within the permanent darkness of the polar craters. Finding ice enables in situ resource utilization, or ISRU. Instead of dragging heavy supplies out of Earth's gravity, crews can harvest what they need directly from the local environment. By applying an electric current to the melted ice through electrolysis, water splits apart. The oxygen is routed into life support systems for astronauts to breathe, while the hydrogen becomes rocket propellant. The confirmed presence of water establishes this world as humanity's most vital cosmic refueling station. Coordinating this extraction effort requires a dedicated command center parked overhead, the Gateway space station. Assembled in lunar orbit, Gateway is an international collaboration combining living modules, telecommunications, and robotic arms provided by space agencies across the United States, Europe, Japan, and the UAE. It functions as an orbital port where arriving cargo ships dock, a deep space laboratory for studying radiation, and a staging ground where crews transfer to landing vehicles. Meanwhile, autonomous machines process pulverized lunar regolith, feeding it into robotic 3D printers to build thick-walled habitats, shielding crews from radiation. By anchoring orbital ports to in-situ surface construction, the moon establishes its role as the primary logistics hub for deep space exploration. All of this raises a heavy question. Why commit billions of dollars and risk human lives to settle a desolate expanse of dust? Launching from Earth demands a massive expenditure of energy to escape its deep gravity. Because lunar gravity is 6 times weaker, that same ascent requires only a small fraction of the thrust. A fully fueled ship launching from the lunar surface can carry much heavier payloads, traveling directly to Mars and the outer planets without fighting the crushing pull of Earth's atmosphere and gravity. The vehicles being assembled today, like the Artemis Space Launch System, carry the legacy of Apollo, but their purpose is different. They are the initial transports built to bridge the gap to deep space. Mastering engineering and resource harvesting on our closest neighbor is the absolute prerequisite for reaching the rest of the solar system. When we pull back far enough, our immediate celestial neighborhood fades into an ocean of stars. The scale of the wider universe is mathematically incomprehensible. It is a dark, freezing vacuum stretching across billions of light years, a system operating with absolute indifference to anything living within it. Yet, against that immense silence, a fragile species born on a blue planet continuously pushes outward, driven by a relentless compulsion to ask why. Our persistent drive to explore and build allows the universe to finally observe and reflect on its own existence.